Okay, what did we discuss last class? Yeah, we defined vector space as the previous the class before that. Yeah, we talked about subspaces. What is subspaces? Yeah, subset and a vector space by itself. Okay, all right. And then, what is a trivial subspace? Yeah, so if you're talking about Rn, zero, just a zero vector is a trivial subspace of Rn. Okay, and then, so this is what we first discussed, and then, what is linear independence? No, what is it? So, vector spaces are sets, subspaces are also sets. What is linear independence?
So when they cannot be expressed in linear combination.
No, it's a property, right? It's a property of a set, right? It's a property of a set of what? Vectors. When do you say a set of vectors is linearly independent? What is the condition? So if we write down if xi are the different vectors in the set, okay, and what is the condition? This is 0 only if 0 for all I. Okay, if there is at least one alpha I for which this is alpha is not equal to 0, then this is a linearly dependent set. What does it mean geometrically or intuitively? What does linear independence mean? What does it tell us about the set of vectors? Right, so if this condition is not satisfied, that means there is at least one vector in that set which can be expressed as the linear combination of other vectors in the set. Okay. That means the information conveyed by the vector can be derived simply by taking a linear combination of the information available in the other sets, other vectors in the set. Okay, and then what did we talk about after that? Right. Span of a set S, set of vectors. What is the span? What is this defined to be? It's simply the set of all linear combinations of the elements of what? Elements of the set S. Okay. Okay, and then inner product. I'll simply abbreviate it as IP. What is the standard inner product? At least for vectors in, so if you have two vectors x and y in Rn, what is the definition of the standard inner product? It's written as x transpose. What is this? That's all. Okay. Then there are some properties that this has to satisfy, but we won't go into the details of that. And then after this, what did we talk about? Norm. What is the idea of a norm? Size or magnitude or the length of the vector. Okay. And we looked at different types of norms. What is the most common norm? The two norm. Let's say x is a vector from. Can you see this? You can read it. Okay. From Rn. What is the definition of the two norm or the square of the two norm? It's simply x transpose. Okay. Okay. What about a general p norm? summation over I. It's not just power p, but the modulus. Okay. And what is the geometry associated with these different? We looked at the geometry associated with at least 3 norms, right? In R2. For the one norm, what does this diamond tell me? What does it tell you? What are all these points? These are all points with the same one norm. Let's say it's equal to 1, some value. What about the 2 norm? What will that look like? So it looks like a circle. It is a circle. Not looks like a circle, it is a circle. 1. And what about the infinity norm? What is the definition of the infinity norm? What is the definition of the infinity norm? Sorry, you'll have to be louder. Okay, absolute value what? There are n numbers, no? You take the absolute value of all of them, and right. Simply the maximum absolute value of all the elements in your vector. Right? Okay, all right. This is where we stopped. Okay, we'll take it. We'll continue from here. Right. The next important idea that we'll talk about is on the idea of the orthogonality of vectors. Yeah. Okay. Okay. And when we say orthogonality, we're talking about whether talking about the idea of two vectors being perpendicular to each other. So if you have two vectors x, comma y, for now we'll only talk about vectors in Rn. You say two vectors are orthogonal, or you express it like this: x perpendicular y. This means that the vector x is perpendicular to y. Okay, and the condition for a vector x to be perpendicular to y is very simple. The inner product between the two vectors should be equal to 0. Okay. Right. That's a definition. You can derive it using the Pythagoras theorem. I won't go into the details. You can work this out yourself. I'll give you how to. So, for example, you remember the 2 norm. So, in what does the Pythagoras theorem tell us? So, for example, if you have and if you're talking about a point in R2, and let's say the components are x1 and x2, the length of this vector is simply, so this is x1, this is x2. The length of this vector is simply square root of x1 square plus x2 square. Okay, that's essentially from the Pythagoras theorem. Okay? But we know how to compute the length of the vector, right? Using the 2 norm. What is the square of the 2 norm? In terms of the inner product, standard inner product is x transpose x. Right? Okay. Now let's look at two vectors. Okay. Vector 1, and let's say there is a another vector. Okay. This is the third vector. Let me do this. So the x vector, so y vector. Okay. Yeah, please. the difference between these two is this. Okay, you can ask what is the length of this vector. Okay, and this you can express like this in terms of the standard inner product, square of this. It will simply be x minus y transpose x minus y. Yeah, go ahead. Yes. Now it turns out you can take the transpose operation inside. So this will be x transpose minus y transpose multiplied by x minus y. Okay, and you simply apply the rules of multiplying two terms like this, and then you will find that you get an expression like that. See, if this is perpendicular, right, then we know the length of this, the square of the 2 norm of this vector will be the sum of the square of the 2 norm of this vector and this vector. That's from the Pythagoras theorem. That means x minus y square should be equal to x square plus y square, right? That means if you expand this, right, that should be equal to this. And if you expand this out, well, I'll do the whole thing. This will be x transpose x minus y transpose x minus x transpose y plus y transpose y. Okay, what is x transpose x? That's this. Plus y transpose y, that's this. The extra term that is left is this, and we know at least the standard inner product in Rn is commutative. That means x transpose y and y transpose x are the same. That means I can write this as simply two times x transpose y. If this is equal to this, then this has to be 0, because this is this term and this one is this term. It means this has to be 0, and that's the condition. That's the reason why it has the inner product or the standard inner product between x and y should be 0 if the two vectors are orthogonal. Okay. Now that is because see, this proof that we've written is general. That means this works for any Rn, not just in 2 or 3 dimensions which we are familiar with. Okay. So see, if the inner product can tell us when two vectors are orthogonal, that means maybe it also captures something more general. When it's not 0, maybe it tells us what is the angle between the two vectors, because when it's 0, of course it's capturing that information, and it turns out it does. So the angle between two vectors in any space, let's say this is in Rn, x, y, you can get that from the inner product, and it turns out this angle theta, the cos of this angle is nothing but x transpose y divided by length of x multiplied by length of y. Okay, maybe you remember this from your 12th standard physics or mathematics, where the dot product between two vectors a and b, let's say this is a, this is b, and this is theta. What was this equal to? What is a and what is b? Yeah, that's simply the length of the vector. So that's, and what are these? That's essentially saying what we're saying, x transpose y is length of x multiplied by length of y into cos theta. Okay, so the inner product does capture angle. If the two vectors have length 1, then the inner product is cos theta. If they are not of length 1, then you have to normalize it by their lengths, because cos theta has to be always between -1 and +1. Yeah. Okay. Right. This also means that your inner product, or the magnitude of the inner product, so that this is a real number, right? This also means if you take the magnitude of this number, so from this expression we have multiplied by y into cos theta. If I take the magnitude, if I ask what is the magnitude of this, that is simply the magnitude of this. Now these are positive numbers, right? That means I can take them outside the magnitude sign, right? without doing a magnitude operation again. So this will be x multiplied by y multiplied by cos of theta. What is the magnitude? What can we say about the magnitude of cos of theta? It'll always see cos theta is always between plus or minus 1. That means magnitude of cos theta has to be between 0 and 1, right? That means this number will always be less than or equal to, right? Because this number is between 0 and 1. Okay, that's essentially that inequality there, which is an important inequality. The inner product, the magnitude of the inner product between two vectors is always less than or equal to the product of the lengths of the individual vectors. Okay. Right. Now with that, that's all I wanted to say about inner products for now. We'll now move on to another very fundamental concept in vector spaces, which is this idea of a basis. Okay. Now to understand this idea, let's say we are talking about Rn. To understand what is basis. Okay. Let's say we have a set of vectors that we've chosen from Rn. Okay. Set of vectors V that have vectors x1, x2, xm. Okay, a finite number of, we've chosen a finite set of vectors from Rn. Okay. Now I take another vector, y. Okay. And let's say y can be expressed as the linear combination of the m vectors that you have from the set V, such that you can express y as alpha I xi. See, whenever I say a linear combination of a set of vectors, you should immediately this expression should immediately flash in your mind. Okay. So let's say I have a vector y that I can express like this. Okay. Now the question is, let's say there is a vector y that can be expressed as a linear combination of set of vectors here. That means this vector belongs to what? The right? Is that right? Right? Because the span is defined as a set of all possible linear combination. It means y must be in the span of V. Okay. Now the question is, if you take a vector from the span of V, I can write it like this by choosing some alpha i's appropriately. Now the question is, are the alpha i's unique? What I mean by that is so there are m different alpha i's. So for this vector y, I have a set of alpha i's. If I know the set of alpha i's, I can reconstruct y using the set B. Now the question is this set of alphas, is that unique for y? Or are there multiple ways or multiple set of alphas that will give me y from the x, from the xi's that I have? Okay. Let's maybe look at a concrete example. Let's say we're talking about R2. Okay, and my set is 1 0. Okay, now my y is 5 0. Okay, now I ask you, what can you say about the alpha i's? Are they unique or not unique? So there is only one x here, so this it's unique, right? The only alpha 1 that will give me y is 5 times. So alpha 1 equal to 5 is the only solution. Alright, now let's consider another example. Let's say I have 1 0 and 2 0, and I ask you the same question, except now you have 2 alphas that you have to choose. This is 2. Now I ask you, are the alpha i's now unique? No? What are the possibilities? Let's say option 1, I can choose my alpha i's to be alpha 1 equals, I can just choose this. Right? Is that the only possibility? No, it's not. I can choose second option, which is alpha 1 equals 1, alpha 2 equals 2. In fact, there are an infinite number of possibilities that I can choose to express this vector from the span of y in terms of these vectors that I've chosen. Okay. So you can see that there are two possibilities. You either have a unique solution provided y is in the span of v. If y is not in the span of v, then of course this does not apply. Okay. If y is in the span of v, there are situations where you have a unique set of alpha i's, and there are situations where you don't have a unique set of alpha i's. When does that happen? When do these two situations happen? When do you get unique alphas, and when do you not get unique alphas? What can you say about these two sets in terms of linear independence? Is this set linearly independent? The first case. How do you verify if this is linearly independent? Go back to the definition. If it's not clear, what is the definition, and simply try and apply the definition. The first case is that set linearly independent, this set. It is, right? So yeah, the only alpha 1 times x1 that will give me 0 0 if alpha 1 is 0, right? So it is linearly independent. What about this? It's not, right? So the condition for getting a unique set of alpha i's is very simple. If the original set that you started with is a linearly independent set, then you get a unique set of alphas. If it's not linearly independent, then you don't get a unique set of alpha. There are an infinite number of alpha i's that will give you any vector from the span of this set V. Okay, this again agrees with what we discussed last time, right? If you say it's linearly independent, there is no redundancy. That means you need all of them. If you say there is no linear independence, that means there is dependence between the vectors. That means there is redundancy. That means I can mix and match them in many ways to get the same information I want. Okay? So that's the idea. And that so if you have a set that's linearly independent, then you get unique alphas. Otherwise, you don't. Okay. That then leads us to this another interesting idea. There is this independence dimension inequality, which basically says, okay, if you're talking about Rn, okay, it says that from Rn, if you are randomly choosing, let's say, set of vectors, okay, so I have my space Rn and I'm randomly choosing set of vectors. I first randomly choose x1 and then I ask, is this linearly independent? As long as this is not 0, it will be linearly independent, okay, because there is only one vector, right? And then I randomly choose another vector and then I ask, is this linearly independent? When will it be linearly independent? As long as x2 is not collinear to x1, then you're okay, then this is linearly independent. Or another way to put it, as long as x2 is not in the span of x1, then you're okay. Okay, then you have a linearly independent set. Now I sample another one, then I ask you the same thing. Is this linearly independent? If it is, what is the condition for this to be a linearly independent set? This new addition that you made. Same thing. As long as x3 is not in the span of these two, then you're fine. Okay. Okay. Now the question is, okay, how long can I keep sampling? Okay, till I hit a limit, or can I keep sampling an infinite number of times and I'll keep getting a linearly independent set? So it turns out there is a limit. Okay. See, of course, if by chance any vector, if x3 turned out to be in the span of this one, of course it will be linearly dependent. Okay? But in case if that does not happen, you can keep doing this. But let's see, after you've chosen n vectors from Rn, and let's say this set was linearly independent, and then this property of linear independence stops there. The moment you sample another one, sorry, plus 15. this for sure is linearly dependent. Okay, which essentially is what is said by that inequality. If you're talking about Rn, you can at the max have n vectors from Rn which can form a linearly independent set. The moment you add n plus 1th vector to a linearly independent set, everything else after that will result in a linearly dependent set. Okay, and that's an important idea. Okay, that from Rn you can only have a set of n vectors which will be linearly independent. Of course, you can have lower. For example, from Rn, if I choose this is a linearly dependent set, but the maximum number you can have is only n. That means in R2, if I randomly sample sample vectors, I can only sample 2. Then I'm done. I cannot sample one more and still be linearly independent. Okay. Right. Let's maybe look at. Maybe I'll come back to this later, not now. Right. So now in Rn, right, if you let's say we've sampled n vectors. Okay. We've sampled n vectors, right? Now with this n vectors, I'll call it S. What will be the span of S? What do you think? And let's assume this is linearly independent. This set is linearly independent. Full of Rn. Why? What can be expressed? When you say all vectors, which vectors? Vectors here. These cannot be, right? This is a linearly independent set. That means any one of these cannot be expressed in terms of the others. See, you're right. The span of this set will be Rn. But I'm asking why. Can you give me an argument as to why it has to be Rn? What will happen if I pull out another vector from Rn and put it here? This will become linearly dependent. That means I can express this in terms of these. That means no matter what vector I choose from Rn and put it here, it can be expressed as a linear combination of the first n vectors. That means any vector that you put here from Rn has to be in the span of S. That means the span of S should be all of Rn. Is that clear? Maybe I was a little too quick, but again, it's not a complicated argument. If you think about it a little bit, it'll start to make sense. I'll leave it at that. So so if you have from Rn, if you have a set of n vectors that is linearly independent, then the span of that set will be Rn, and that brings us to the idea of a basis. Okay, a basis for, let's say, Rn for now. Let's talk about general vector spaces later. For Rn is simply a set of n vectors that are linearly independent. So, if you have a set of n vectors from Rn that is linearly independent, then that is a basis for Rn. And all that means is using those n vectors, you can get any vector in Rn. Okay? If you have any set like that, that is called a basis for Rn. Okay? And that also means that any vector in Rn can be uniquely expressed in terms of these vectors. Okay? See, because if instead of just having n vectors, let's say I had n plus 1. Okay? The span of this is still Rn. Right? This says that I have more than what I need, because xn plus 1 can be expressed as the first n vectors. So the span of this will still be equal to Rn. But the issue is this is not linearly independent. Okay? But if it is a basis, then by definition it has to be linearly independent. If it's linearly independent, then any vector from the span of that set has to be uniquely expressed as we saw here. Right? There is only one, so if it's a basis, there is only one way you can express any vector from Rn in terms of this basis. Okay? So if I choose any y that belongs to Rn, then there is only one way I can write this. The alpha i's are unique. Okay, that means the alpha i's are actually another way of saying the same thing as y. Okay, alpha i's are another representation for y. Right? So y and the set of alpha i's essentially tell you the same thing. Okay, except the two of them are except alpha i's are numbers that you use with the basis s to get y. Okay. Or another way to say that is the alpha i's are basically the expansion of y in the S basis. Okay. Another way to think about it is like this. Okay. Let's say I have 2 points in B. Okay. I ask you what is the distance between A and B. Okay. Let's say you bring a regular ruler, a wooden ruler. You place it here and you say, oh, it's 29.1 centimeter. Okay. Somebody else brings another ruler which measures things in micrometers and says, how much will they say if it's in micrometers? 10 into 10 power 5 micrometers, is that right? Or something like that. Okay. Both of us are talking about the same thing. The difference is your reference and my reference, or the reference of the two people are different. Okay. Both 29.1 and this 29.1 into 10 power 5 are talking about the same thing. This. Okay. Only difference is this is with a different reference. That's the same argument applies here. Your alpha I is simply another way of looking at y. Okay, what way? Using this, using s as my scale. Not we'll talk about what is the original scale for y, but we don't have to worry about it now. Okay, so that's the idea. Another term for the alpha i's are these are called the coefficients of y in the s basis. Okay, so if somebody says these are the coefficients of a vector in some basis, you know exactly what that means. These are the scalars that go in front of the linear combination for you to reconstruct the original vector. Yeah? Okay. Right. So now, if you have a set of vectors S for Rn from Rn, that is the basis. Okay. It turns out that okay. Firstly, for any vector space for Rn, how many bases do we have, or how many bases can we have? Sorry. No, sorry. Not. See, each basis will have n vectors. I'm asking how many. Okay, maybe these x1 to xn, that's one basis. Maybe there is another set of n vectors that I can choose from Rn, which is linearly independent. That will be a basis for Rn. How many such sets can I choose? Infinite number of them, right? There are infinite number of bases. Okay, but it turns out some bases are special. Okay, and the most special one, at least as far as this course is concerned, are bases that are orthonormal. Orthonormal bases. Okay, that is very simple. You have a set of vectors S, x1 to xn. We say that the the set S is an orthonormal basis for Rn if xi transpose xj, if I take the standard inner product of any one of these vectors with another vector, this is equal to 0 when I is not equal to j, and it's equal to 1 when I equals j. What does that mean geometrically? So the inner product should be 1 only when I is equal to j, when xi and xj are the same vector. If they are not, then it's 0. What does it mean? Right, exactly. It simply means that each vector is perpendicular to every other vector and it has length 1. Okay, and if you have this, it's very nice to have an orthonormal basis, and we'll see why. Okay. See, it's nice to have an orthonormal basis because it turns out computing these alpha i's is very easy. Okay, see, for example, we talked about this whole thing saying, oh, if you have a basis, then you can express any vector y in terms of these numbers. Then the question is, how do you compute these numbers? Let's say I do have a basis and I want to compute these. It's not immediately clear how you do it. Okay, but if you have an orthonormal basis, it turns out that finding out those alphas can be done with the tools that we've seen so far. Okay, let's see how. Let's say you have a vector y from Rn because S is a basis. Okay, that means I can express y as, right? I can do this. Now, if you take, let's say we take the inner product of this y, the right hand side and the left hand side with respect to one of the basis vectors. Okay, so we take xi, it's to 1, x1 transpose y. We do the same thing here. Alpha I xi. Remember, the inner product is distributive. That means you can take it inside. What will happen when you take it inside? Let me expand this. So this will be alpha 1 x1 transpose x1 plus alpha 2 x2 transpose x2. Sorry, x1 transpose x2. Alpha n x1 transpose xn. Right? Can we do any further simplification here based on this? You have these inner products, right? Whenever I is not j, it's 0. That means n minus 1 terms here vanish, and all you're left with is this 1 x1 transpose x1. But what is x1 transpose x1? It's 1, right? That means your alpha 1 is simply the inner product of a standard inner product of your any vector y that you're interested in with the corresponding basis vector. Okay, that means if you have an orthonormal basis, then computing the expansion coefficient xi simply requires an operation like this. Okay, that is why these are nice to have. Orthonormal bases are orthonormality for a basis is a nice property to have. See, now that we've discussed this, maybe now you can tell me, again, going back to going back to physics, we used to write stuff like this. What do you think is going on here? Based on our discussion on basis and all that. This is exactly this. You're saying y is a linear combination of your xi's with some scalars here. That's what you're saying here. This vector A is a linear combination of 3 basis vectors, the vector along the x-axis vector along the y axis and the vector along the k axis or the z axis, and these are your alpha i's. Okay. I hope you can connect the ideas together with this. Okay. Are there any questions? This one? Okay. You got this is okay? You're comfortable with this? Now the question is, okay, we started with this and then we've ended up with a slightly more complicated looking expression. The question is, can this be simplified further? Because it's an orthonormal basis, right? No, here, when I say orthonormal basis, these vectors that I have in my set, which form a basis, they are mutually orthogonal, okay? And all of them have length 1. That is what is captured by this expression here, right? If I is equal to j, there is xi transpose xi, that's simply the 2 norm of the vector. The answer you get is 1 because it's of unit length. But if I is not equal to j, it will be 0, right? Now look at this. This is, I've taken the inner product with respect to x1. So I get alpha 1, x1 transpose x1, plus alpha 2, x1 transpose x2, and so on and so forth. The I and j are the same here, and the I and j are not the same in any of these terms. That means they all will vanish because they are all 0. When the I and j are equal, then that inner product is 1. So this also vanishes. You are left with just alpha 1 that is equal to this.
Why is the linear combination of x?
Right. Why is the linear combination of? If you have an orthonormal basis, you can compute these alphas very easily. That's essentially this. Yeah. That is the only advantage you get is computing these alpha i's is very easy if you have an orthonormal basis. If you don't have it, for example, here, if you have again R2, maybe I should not have done this. Yeah, it's fine. Let's say this is my x1, this is my x2, and I have an arbitrary vector y. Okay, I want to express y in terms of linear combination of these linear combinations of these two. Okay, that means I want to do this alpha 1 x1 plus alpha 2 x2. But then, what values do I choose for alpha 1 and alpha 2? That is the question. Because this is an orthonormal basis, alpha 1 is nothing but x1 transpose y, and alpha 2 is simply okay. But if I had this, then this is my y. How much of x1 do I choose and how much of x2 do I choose so that the linear combination of those gives me y? It's not. So it's not as easy as here. You can still, one way to do that is to apply again the parallelogram law of addition of vectors. If you expand this out and then form a parallelogram with these two vectors so that the diagonal the diagonal vector is this, and that will be your alpha 1 and alpha 2. But finding those, that operation algebraically is a lot more complicated than just taking the inner product between two vectors. That's why an orthonormal basis is preferred. Okay. So this then brings us to the. That's fine. I'll skip this. To the idea of the dimension of a vector space. Okay. Okay. Let's say I have a vector space V. General vector space. Let's say not Rn. Okay. How many different types of bases do I have, or how many basis sets do I have for this vector space? Sorry. Infinite number, right? There are infinitely many possible bases for a vector space. Okay. But then the question is, all of them are bases, so there is something common about them, right? It turns out that common feature is essentially the number of vectors that you have in that vector space. Sorry, number of vectors that you have in that basis set. For example, let's say S1 is a basis for V, S2 is a basis for you, so on and so forth. There are infinite number of bases. But it turns out what will be common among all of them is, of course, they will all be linearly independent sets. They will all span V. But there is also one more feature that is common to all of them. That is the number of elements they have. Okay, and the number of elements they have will essentially be the dimension of the vector space V that you're dealing with. Right? For example, if you have Rn, the dimension of Rn is n. That's because a basis for Rn will have n elements. Okay, that means if I have R2, the dimension of R2 is 2. Okay, it's a two-dimensional space. If I have just the real line R, the dimension is 1. Okay, I hope you get that idea. Now this brings us to the idea of subspace, dimensions of subspaces. Let's say we are talking about R2. Okay, I'll call it V. So is V a subspace of R2? Why is it a subspace of R2? Hey, hold on. Sorry, repeat that again. Okay, it's very easy to put these terms together, and usually the sentence you make will not make any sense. Okay, so you have to be very careful about what you say. Yes, V is a subset of R2. Done. It's a vector space because if I take any vector, do scaling or addition, I will remain in the set. So it's a vector. Okay. What is the dimension of R2? It's 2. Now I ask you, what is the dimension of V? How will you find out the dimension of V? It feels like it should be 1, but why? Why should it be 1? Or why is it 1? It is 1. Why is it 1? Go back to the definition of what a dimension is, what I just said. Number of elements in a basis for that vector space. How many, okay, let's say this vector space is defined like this. Alpha, alpha, I don't want to confuse people. A is a real number. Okay. Can you tell me a basis for this vector space? V. No, when you say basis, it's a set. It has to have a bunch of vectors inside, and that set has to be linearly independent, and it has to span the space, the vector space that you're talking about. I'm talking about a basis for V. That means a subset of V which is linearly independent and spans V. Is this a possible basis for V? Is this linearly independent? It is linearly independent. If I multiply by alpha, the only way I'll get 0, 0 is if alpha is 0. Okay. Does it span V? Can I get any element from V from this vector? I can. If I simply multiply by any number A, then I get all possible, and I can choose any A. That means I can get all. That means this is the basis for V. Now you can tell me what is the dimension. How many elements does this basis have? No, 1. It only has 1. This whole thing, this vector is an element of this. That means the dimension of is 1.
Okay. But can't we interpret it in this way that because it is in a two-dimensional space,
right?
its dimension should be 1.
No. R2 is a subspace of R2, right? I mean, it's trivial. But the dimension of that is not 1, it's 2. Okay. What about the trivial subspace? What is the trivial subspace? What do you think is the dimension of the trivial subspace? It turns out the dimension of the trivial subspace is 0. There is no degree of freedom. You can't move anywhere. You're just stuck at that one place. If you have a line in R2, you can move along one direction freely. If you have R2, then you can move along to, I should not say, you have an additional degree of freedom. Now, that brings us to the idea of R3. Okay. Right. Okay. What is the dimension? So, R3, dimension of R3 is 3. What is it? Is the red line a subspace of R3? Assume it extends all the way to infinity. Is the red line a subspace of R3? It is, right? It passes through the origin. It's a subset. It's closed under linear combinations. What is the dimension of the red line subspace? 1, right? If you just get one vector from that set, you can simply get every other element from that set by simply scaling the vector. What about the blue plane? Is that a subspace? It is. Okay. What is the dimension? It's 2. That's because you need 2 vectors from that set that are linearly independent to get every vector from that subspace. Okay. Okay. All right. I hope that's clear. Right. But with that, we're done with all the major definitions. Then we'll look at the last topic, which is linear functions. Okay. What is a function in general? Mathematical function. Let's say G. What is a function? Right. That's the intuitive idea. Formally, more rigorously, what is the definition? It's simply, for example, if let's say you have two sets A and B. Yes, it's simply a map between elements from here to elements here. Okay, so okay, and that's usually the symbol. This simply means G is a function that maps elements from A to elements in B. Okay, the only restriction is every element here can only point to one element here. You cannot have two arrows. Okay, but you can have this. Two elements here can point to the same element here, but what you cannot have is one element here giving you two elements from here. Okay, that's the only restriction. Otherwise, that's the general idea. Okay, so this idea of linear function is simply this: f is a linear function if it maps elements from Rn to R. That means it simply takes elements from this huge space and then maps it to the real line. Okay, that means every element here will point to some number on this line. Okay, okay, but that does not make it linear. Okay, this is simply a function that maps from Rn to N. This function f is called linear if it satisfies the property that I've said here. That's simply superposition. Means if I choose a vector from Rn, okay, then I get a number y. Okay, notice that y is a scalar here. Okay, x is a vector, y is a scalar because we're dealing with this function which maps from n vectors to a real number. Okay, this is linear if it satisfies the superposition property. Let's say I have a vector x1 and vector x2, both of which belong to Rn. And let's say if I apply the function f to x1, I get the number y1. If I apply the function f to the vector x2, I get the number y2. This function f is linear if I apply the function f to a linear combination of x1 and x2. The mapping that I get, or the number that I get out, will simply be alpha 1 times y1 plus alpha 2 times y2. Okay, if this is true for all possible x1 and x2 that you can choose from Rn, and for all possible alpha 1 and alpha 2, then this function is said to be a linear function. Okay, that maps from Rn to R. Is that clear? See, another way to think about that is simply this. You have a function that maps some vector in between this parenthesis to some number y. Okay. If what is inside the parenthesis is a little bit more complicated like this, it's not just some individual vector, but a linear combination of two vectors. Okay. If f is linear, it simply tells you that you can move this f to the inside. That simply means I can write this as alpha 1 times x1 plus alpha 2 times x2, and I can simplify it even further. In fact, I can bring the alpha out. Okay. If you had a non-linear function, you cannot do that. If it's linear, you have this nice freedom of taking this f inside. Okay, or being able to work on each of these elements individually. Okay, that is the advantage we get. So that is a nice thing about a function being linear, because it simplifies some of this stuff. Yeah, that's the definition. And then the very last thing I wanted to say, and it turns out, and this again is a very interesting consequence of the definition of linear functions. If you have any function f that is linear, okay, it turns out any linear function that maps from Rn to R, okay, can be written down like this. Okay, where W is again some other vector. This is a constant. So if f is some fixed function, okay, let's say somebody is given you this black box, and they say this is this function f, and if you give any vector from Rn here, this box will simply spit out a real number. Okay, and this apparently this black box satisfies linearity. That means it satisfies this. It satisfies the superposition property. If you have this black box and you hate this black box, you don't want to use it, you don't have to. If it's linear, all you have to do is identify some vector w, okay, from Rn, take the inner product of that vector with the input that you're giving to this black box, and the output of this operation will be exactly this, what the box would spit out. Okay, how you would identify w, that's part of your assignment problem. But the reason you're able to do this is because of this linearity property. Okay, so for now, just remember that any linear function that maps from Rn to R can be expressed like this. In the next week's lecture, we'll see that if you, you can generalize this. Why do you only want stuff mapping from Rn to R? You could say, I want something, I'm interested in something that maps from Rn to Rm. Okay, and it turns out that any linear function that maps from here to here is represented by a n cross n matrix. Okay, so this is just a generalization of this idea, because this W transpose is simply a 1 cross n matrix. Okay. Okay. With that, we stop with the lecture. Sorry, it took a little longer than I had expected. Maybe if you have any questions now, we'll discuss them. Otherwise, we'll go through the tutorial problems, and then we'll have a quiz for 10 minutes at the very end. Are there any questions? Yeah, can I have it? Okay. Are there any questions so far? No? Okay, let's talk about the first problem, which is so the first question is essentially a question on finding out whether or not the different sets that are given to you are vector spaces or not. Okay, the first one is a set like this: a1 x1, a2 x2, where x1, x2 are real numbers, and a1, a2 are some fixed real numbers. Okay, this is some set S. Is this set a vector space? How do you go about finding out? Sorry. Oh, sorry. Yes. Sorry. Yeah. That means set of all real numbers x1 and x2 for some fixed value a1 and a2, such that this expression is 0. How do you go about doing this? Then you have to find out if it's a vector space. You simply apply the two rules. That means, sorry? Yes. So you simply apply the two rules. It should be closed under vector scaling and vector addition. Okay. Okay. How do we verify vector scaling? See, any x1 and x2 that you choose. See, maybe the way I've expressed this is not is maybe not correct. Let me re-express this. Okay, set of a vector with set of elements like this, such that a1 x1 plus a2 x2 equals 0, where x1 x2 are real numbers, and a1 a2 are real numbers as well, but they're fixed. Okay, this is a little bit. I think this is cleaner. Okay. Now, how would we verify vector scaling? Okay. Well, let's say we choose an element. Okay. Let's say that element is x1, x2. Okay. We know that this is an element from this set because this is true. Because these two numbers x1 and x2 satisfy this. That means this is a vector from, this is an element from here. That means a1 x1 plus a2 x2 is 0. Okay. Now all I have to verify is if I scale this vector by some alpha, does that alpha times this element, is that still in this set? For it to be in this set, that scaled vector has to satisfy this equation, and that is all we have to verify. Okay. What will be the scaled version of this vector or this element? This 2 vector. So we multiply by alpha x2. That means it will be alpha x1. Now the question is, does this satisfy this equation? Well, for this vector to satisfy this equation, all you have to verify is whether a1 alpha times x1 plus a2 x2 is this equal to 0. Alpha is common there in both of them. That means I can pull the alpha out. This is alpha times a1 x1 plus a2 x2. But I know a1 x1 plus a2 x2 is 0 because the original vector came from this set. Right? This is 0. That means this is alpha times 0. That means this is 0. It means it does look like this set is closed under vector scaling. Is that clear? Okay. What you can tell me about vector addition? How will you verify vector addition? Let's say I call this x. If x is in this set, alpha times x turns out to be in this set as well. Now you can verify addition by using maybe 2 vectors v and w that come from the set. Let me write it down. So V will be V1, V2, W would be V2. Is this set closed under vector addition? See, if V and W are from this set, we know two things for sure. A1 V1 plus A2 V2 is 0, and A1 W1 plus A2, you know these two are satisfied. What vector do you get if you add V and W? No, what vector do you get? No, I'm not applying this. Plus W1. What condition does this vector have to satisfy for it to belong here? A times this plus A1 times this plus A2 times this should be equal to 0. Is it 0? So let's verify. A1 times P1 plus W1 well, real number multiplication is distributive, so A1 V1 plus A1 W1 plus A2 V2. Now if you, these two will add to give you 0, these two will add to give you 0, that means this is 0. That means it is closed under vector addition as well. Okay, so it's closed under both of these, so it turns out that this is in fact a vector space. Yeah, is that clear? Again, all we've done is blindly apply the two conditions, that's all. Is the 0 vector in this? I mean, it has to be because it's a vector space. It is, right? If you simply choose these to be 0, this is still satisfied. Okay. You can now tell me about this, how to solve the second problem. Shall I write this off? Or I'll use that. The second problem is, again, a set of vectors. I'll again reformulate. I don't like how I've written it there. Set of elements like this. X belongs to Rn such that A transpose X is 0, where A is in Rn and this is fixed. This is R. Is this a vector space? Follow the same logic that you followed here. We'll start with the first one. You can tell me about scaling. Sorry, equal to B, is it? Fine, let's do 0 first. We'll do the B after that. If this is confusing, remember X is x1, x2, xn, and this vector A is nothing but a1, a2, an. Okay, and what is A transpose X from the definition of inner products or standard inner product? AI, that's all. And this is equal to 0. it's closed under vector scaling. Yeah. If you multiply this by alpha, each of these term gets multiplied by alpha. Alpha comes out. What is inside the bracket is 0, so this is still 0. And you will find this is also closed under vector addition. Okay, it's exactly the same as the previous problem, except that was from R2. This is from Rn. Okay. Okay. If that is clear, now what happens if we change this by B? B is some non-zero. B is again from Rn. This is fixed, and B is not equal to 0 vector. Now here this would be, this is equal to B. Let's do it. Okay. Let's say we've taken X from this set. Okay. That satisfies this expression. Okay. Now what will happen if you scale X by alpha? What you have is right. For this vector to be in this set, these elements have to satisfy this expression. Right? If we, that means A transpose alpha times X bar should be equal to B. Okay, let's verify if it's equal to B. What is this equal to? You remember from the inner product property, if you multiply one of the vectors by, it comes out, right? So this will be equal to alpha times A transpose X. What is A transpose X? It's B. So this is equal to, hold on. If you take X, A times A transpose X gives me B. But if I scale it, A transpose alpha times X does not give me B. That means this is not closed under scaling. That means it does not belong here. You don't have to do any work. This is not a vector space. Okay. I mean the difference between the two, if you remember, these were subspaces of R2. These were all things that were passing through the origin was a subspace of R2, but not this. If it did not pass through the origin, it was not a subspace. That's exactly, this is exactly this, but in Rn. This is a hyperplane in Rn that does not pass through the origin. Whereas if B was 0, then it's a hyperplane that passes through the origin. Okay? Hyperplane is simply a plane in a higher dimension. That's all. Okay. What about C? The next one. Sort of again, I don't like it. Sorry, I'll be explicit. That's the set. It's not why. You'll have to tell me why. It's not, but you have to tell me why. What happens when you do scaling? So if I take X, that satisfies this. What happens if I take alpha X? What do I get? Will you get alpha? So, alpha times? See, X transpose X is 1. But if you scale the vector, we'll get alpha square X transpose X. So it's not, this is not equal to 1, this is alpha square. Okay? So this is not a vector space. And this, what is this? We saw this in R2. This was a circle. If it's n is 2, this is X transpose X equals 1 is a circle. This is a hypersphere. Not 2 alpha, alpha square. Sorry? Is it clear? What is the question? No, yeah, here. See, X satisfies this property. Okay. I'm asking, does alpha X satisfy this property? Alpha X is your vector now. This whole thing is X. And because X appears 2 times, means you're asking whether this satisfies this property. That is why you get these 2 alphas. Whereas there, only 1 alpha appears because you only have 1 X. Yeah? Is it clear? Okay. Okay. The next one. Okay. Next one is a little bit more strange than what we've come across so far. Okay. This is simply the set of all polynomials of order 2 or lower. Okay. Here, the thing that varies here are the A0, A1, A2. Okay. So if I pull out something from here, the element that I'll get can be 5 plus 2x plus 3x square. That's an element from here. If I pull out another one, maybe I get minus 3x, where x is any number from 0 to 1. Okay, so I really have this polynomial expressions, okay, from this set. Okay, and now I'm asking this weird question, asking, is this a vector space? Okay, this looks nothing like the vectors that we've seen so far. Okay, that's because the idea of a vector is more general. This idea of a set of numbers being a vector, we started out with that because it's easy to wrap our head around something like this. But the real beauty of this subject is it goes beyond just a set of numbers. It turns out, if you have a set of polynomials like this, they also satisfy in fact, this is a vector space. Okay? It turns out this also satisfies the same properties as of a vector space. That means all the geometric intuition that you have about a set of n numbers like this equally applies here. That means you can think of a polynomial as a vector in some polynomial space. Okay, because it behaves like, because it satisfies the properties of a vector space. Okay. Now the question is, does this it is a vector space, but we'll have to show that it's a vector space. Okay, we do the same thing, and the standard rules for arithmetic of polynomials apply here. Okay, if you choose any element from this set, let's say this is the element we choose. It's a polynomial where a0, a1, a2 are real numbers. Okay, that is the property. Okay, any second order polynomial of order 2 or less with the coefficients that are real numbers. That is the property that defines this set. Okay, now this is, you will agree this is an element from that set because a0, a1, a2 are real numbers. Scaling would simply mean I multiply this vector, this is a vector, okay, by some real number alpha. If I multiply by alpha, what do I get? So I get alpha a0 plus alpha a1x plus alpha a2 x square. Now the question is, does this belong in this set? What is the condition for this to belong in that set? It has to be a polynomial of order 2 or low, true, and its coefficients have to be real numbers. Are these real numbers? These are real numbers. That means this is there in this set. Okay. So this set is closed under vector scaling. What about addition? Let's say we choose two elements, a0 plus a1x a2x square. That's the first element. The second element is, let's say, b0 b1 b2 square. These are two elements from the set, and if I add these two and apply the standard rules for adding polynomials, what do I get? I'll get a0 plus b0 plus a1 plus b1 x plus a2 plus b2 square. Does this polynomial belong here? It does. That means this is also closed under vector addition. That means this is a vector space. Okay. Now you could ask, does this mean that I can talk about the inner product between two polynomials? You can. Can you talk about two polynomials being perpendicular to each other? You can. All the geometric intuition that you had about vector spaces or these n vectors equally applies here. Okay. We'll just look at one more. We won't do the quiz because we are out of time. We'll do it first thing tomorrow on Monday. Yeah. Okay. Monday, right? Yeah, Monday. Monday. Yes. Yeah. Okay. Yes. So people who are not here on Monday. Oh yes, Pongal. Okay, we'll have it on Tuesday. We will still have the class. We'll record it and then you can view it online. I will try and upload it by Tuesday morning. Okay. Okay. The last one. This is a little bit more straightforward. Now, because a set of n elements, n vector, set of this forms a vector space. That means if you, any time domain signal we record for practical purposes, right? It's a finite length. That means, and it's all sampled and digitized. We don't work with continuous traces, but sample versions of signals. Say I have a signal like this. This is of interest to me. What I record is simply the value of the signal at different time points. Okay. For some finite duration of time. That means I really have a finite number of numbers, right? Which I can write like this. Let's say I have n numbers. That means I can think of this as an n vector. That means now I can think of time domain signals of a particular length as vectors in vector spaces. That means I can think of signals as arrows pointing in some I-dimensional space. That means algebra, now you can think of algebraic operations that you do on these signals in geometric terms as well as simply manipulating vectors in some high-dimensional space. Okay, that's what the last question is about. And we'll see you can talk about orthogonality of two signals and basis for signals, expressing some signal like this as a linear combination of other signals and all that. Okay, and just for your information, so you remember we talked about Fourier transforms in the very first lecture. It turns out that the Fourier transform is simply a process of changing the basis from standard basis to a Fourier basis, and the Fourier basis is in fact an orthonormal basis. Okay, so the ideas that we've covered in this class are really important because these are all going to come back as we go forward. Okay, so we'll stop with that. You can attempt the other problems as well. If you've understood things till here, the others should be something you can attempt as well. And then we will release assignment 1 by later today or tomorrow morning. Are there any other questions before we close? Nothing? Okay, alright, thank you. See you guys Monday.